Hello, Physics 20s. Welcome to uh, another little video here. Sorry, I'm juggling with some stuff. I want to actually talk about power and efficiency today. And I do want to show you a couple of things that will help you understand the formulas behind power. So, power is a really natural extension of what you've already been learning about work and energy. Um, Power is defined as the rate of doing work. So the issue that we're just going to add to everything we've been doing is time. Okay. So it's really power, P, is equal to how much work you do or how much energy you convert per second. Okay. And the units are named after James Watt. And actually, that's what I was going to show you right here. Um, James Watt, inventor of the steam engine and a number of other devices, but he gets credit for actually trying to measure the amount of work done. And in his day, all the muscle in his day, they didn't really use too many machines, or they were just starting to. And James was trying to convince people to buy his machines, and he had to come up with a way of measuring their output. And so what he did is he compared it to a horse. And as you can see here, what he did is he took an average horse and he measured he measured the distance that a horse would have to walk horizontally while pulling a a mass up a mine shaft. Okay, so you can imagine a really deep mine shaft, and you fill it with coal, and then you use a horse and a pulley system like this to get it out of the mine shaft. Um, Famously, these are rough numbers, I think, on what he actually measured. For 100 feet of distance, a horse could pull 330 pounds of coal vertically 100 feet in 1 minute, so 60 seconds. Okay. Now, obviously, there's a ton of variables here because it depends on the size of the horse, and obviously the load could be kept the same. So it was an approximation, but it turned out to be a very useful measure of what became known as power output or power, because the horse would cause a change in the gravitational potential energy of the coal. It would raise it from the bottom of the mine shaft up 100 feet. So to do that requires work, and the horse did that in 60 seconds. So you kind of get a picture of just how, like anytime you do work, the amount of time that it takes. If you factor that time in, you can calculate power. And power, as you saw in the notes, power is measured in watts. But a watt is a joule second. Okay, so 1 watt is 1 joule of energy per second. So this opens, and I'm just going to blast through all of these. This opens a kind of a cascade of possible formulas for power. Okay, because power is the work done per unit of time or the change in energy per unit time. And the classic one, like the horse raising that coal out of the mine shaft, that would be a change in energy of gravitational potential energy. And technically, we could throw a delta in there because it would be mg delta h divided by the time in seconds. Now, that's not on your formula sheet, but you can add it if you want, because it's a very common calculation when you're determining power, because it's relatively easy to measure how long it takes to raise a mass up a certain height. And that way you could do a power calculation. Okay, so another variation, though, these are all equal signs, right? Another variation, you could expand the work formula, force times distance divided by time. Okay, and if it's a vertical distance, that's fine. But that's one way you could calculate power. And this is another, or what you might see if you were looking at this, we have distance over time right there. And if you have distance over time, distance divided by time is velocity, or displacement divided by time is velocity. So if you have a constant force and you have a constant speed or a constant velocity, you could calculate work by multiplying the force times the velocity. Okay, so it has to be a constant velocity. Obviously, if you're accelerating, then it's a little more complex, but we're not going to go that far. But based on this simple derivation, there are at least 3 variations to the power formula. So when you calculate power, your units will be in watts, and you can get kilowatts. That's a term you may have heard of. 1,000 watts is 1 kilowatt. There's 1,000 watts in a kilowatt. And obviously there's megawatts and gigawatts. And actually, just a fun note here, because I'm really fascinated with electricity. Power companies will take this formula here and they will rearrange it to this expression for energy. Energy equals power times time. And if you measure your power watts, a watt is not a lot of power. I mean, you guys are familiar with light bulbs, 60 watt, 100 watt light bulbs. Those are actually starting to, we'll talk about light bulbs in a minute, but those are starting to become obsolete. Power, if you measure power in kilowatts and you measure the time not in seconds, but in hours, then you get a new unit, and it's called, you can measure energy in kilowatt hours. And the reason I like mentioning that is because that's typically the measure of a battery for an electric car. The power output's measured in kilowatt hours. So connected closely with power, which we're going to get some practice with power, but connected closely with power is a second principle called efficiency. And I'm confident you've done some of this in your science classes in the past. Efficiency is the ratio of energy or useful energy output divided by energy input. So it's always out over in, output over input. And it's expressed crucially as a percent. Okay, so actually, yeah, what's missing from these formulas? It's efficiency is output over input, but you'll get a ratio, you'll get a decimal with that, and it should be times 100%. I did that on the formula sheet. You'll see that when you look at it. There's 2 places: energy output over energy input times 100. Or now I know we're just learning this, but you can also do it with power. So power output over power input. Okay, so just go slowly when you see that it's a power question. As soon as you see W's like watts or kilowatts, you know you're dealing with power. So just let your brain go to the power formulas. But for efficiency, though, let's just take a minute on efficiency. Efficiency has an interesting evolution when you think about lights. Incandescent light bulbs were standard for a long, long time. All throughout my lifetime growing up, incandescent light bulbs were the standard. But over time, fluorescent lamps started to become useful, and they were the long tubes, and we actually had those in our school for the longest time, even. In our hallways, in our classrooms, we had the fluorescent lamps. Compact fluorescent lamps, those are like the DQ swirl glass tubes that use the same technology. But as you can see, and then of course we have LEDs now. So as you can see here, these are rough numbers. Depends on where your sources and the timing of some of these when these were manufactured. But as best as I can get for some numbers, incandescent light bulbs are basically 2% efficient. That means that 98% of the energy coming into a light bulb is lost as heat, an incandescent light bulb. And a lot of you may have even had those easy bake ovens when you were a kid, and they used an incandescent light bulb to do the baking because they pump out so much heat. Anyway, but yeah, compact fluorescent lamps kicked in probably in the last 15 years or so or longer, and they emerged as a more efficient option. They're around 10% efficient, which is much better. And then LEDs really have taken off in probably the last 10 years. They are much more efficient. They use way less energy than the other 3. And as a result, they are quickly taking over the lighting industry. So here, I'm just going to show you this. This is, I'm really excited about what's happening in our school, because when you come back, all of the lights in the classrooms and the hallways are now LEDs. They've switched them all. Our gymnasium had them switched about a year or so ago, and now every light in the school is an LED. So there's no surprise that that's happening, as you can see here in this little graphic. The efficiency of LEDs is much higher than all the others, and the cost goes way down, and they last so long. They last, oh my goodness, some of them, depending on, they can last 10 years or something like that. The duration is incredibly long. So in terms of efficiency, LEDs are just crushing it in the industry. Almost, in vehicles, almost any light you come across now is going to be an LED. And the longer we move forward, that's going to be the case. So anyway, so let's actually just do a couple of these questions. Oh, yes, sorry. I guess this next part, I did already highlight that power and speed. If you're moving at a constant force, there's the expression right here, but we already showed you that a bit earlier through the derivation I did up there in red. So power can be calculated by force times distance. So here we have an elevator, and it's moving its occupants 1,300 kilograms. It moves everything to the 12th floor. So that's a distance of 40 meters, and it does that in 75 seconds. So we've got those three numbers. Then it wants the power output. Okay. So crucially, what I'm hoping you'll see is power. One way you can think of it is power is equal to the change in energy divided by the time. Definitely, when you see a question like this, does this mass experience a change in energy? Absolutely. It goes from the ground floor up to the 12th floor, and it does that in 75 seconds. That's a change in energy of gravitational potential energy. That would be mgh divided by the time. And if we substitute in those numbers, basically 1,300 kilograms times 9.81 meters per second squared times 40 meters divided by 75 seconds, that gives us 6,801.6 watts. Okay. Now, again, I didn't write in the numbers, but just for sake of space. So what you should be comfortable with is, if you get a number like this, we could just as easily express this in kilowatts. So all we have to do is divide this by 1,000, or some of you can see that, take the decimal. Oh, it won't let me do that here. Take the decimal and move it over 3 places, and we would get 6.8, I guess we could get 6.81 kilowatts, okay, if you wanted to answer it that way. But that would be the output, okay? Now, I kind of, let me just clear this off here so you can see that. So now it says, what's the efficiency of the system if the motor must generate 9.4 kilowatts? Now, generate is a tricky vocabulary word in this context. Sometimes you might interpret that to be the output. For our purposes, when you see the word generate, that means input. That means how much goes into the system, okay? And just as a general rule of thumb, I'm sure you remember this as well, output is always less than input. Okay, you can never get more than 100% efficiency. That's basically a violation of the conservation of energy, okay? So you can see 9.4 kilowatts is bigger than 6.81, if that helps you, okay? But 6.81 is the amount of power needed to do the job, but or I guess maybe that's not a good way of saying it. That's how much is required to do the job, but you need more than that, because you're dealing with a system, you're dealing with an electric motor or some type of motor that's not 100% efficient. No motors are 100% efficient, although electric motors are awesome. They're like pushing 90, 95% efficient, versus an internal combustion engine is, more like 12 to 15% efficient. So anyway, so yeah, the efficiency then, we would say, is equal to power out over power in times 100, of course. Okay, so when we do that ratio, it would basically be 6.81 kilowatts over 9.4. actually, I think when I did this calculation, I didn't round it to 6.81. I left it as 6.8016 or whatever. But anyway, so that came out to, it comes out to 0.724 before I multiply by 100. Okay, so you can see you get a ratio. So multiplying that by 100, you get 72.4%. Okay, so just remember, I don't think efficiency is too bad. Just remember that when you calculate it, it should be as a percent. Okay, so yeah, I think, yeah, well, I guess let's do this one quick too. All right, so a free body diagram on this mass, it's 2,000 kilograms, it's traveling up a hill at a constant speed of 25 meters per second. Okay, that is a big clue. That's a constant speed. Okay, I know it says 90 kilometers per hour, but we converted it for you. The force of resistance which opposes the motion is 450 newtons, and the slope is 6 degrees. Okay, so this slope here is 6 degrees, and there is a force of air resistance acting on the mass. So from there, there'd be a force downhill of 450 because it looks like it's going uphill. Okay, so there is a force going uphill that we don't know, and there's at least 450 newtons down. Now, so if it was going at a constant speed, then all the forces have to be balanced. And that's a really important principle to catch as soon as you know that it's going at a constant speed. If there was no other forces acting on it, then the applied force would be 450. But what we know from this, and I'm going to add this in red, we know that gravity is acting on this guy, and that he has two components. He's got a force of gravity perpendicular, and he's got a force of gravity parallel. Okay, and yes, the normal force would match the force of gravity parallel. So, meaning, of course, that the normal force and the force of gravity perpendicular, sorry, I think I said that backwards. The normal force and the force of gravity perpendicular, they would cancel each other out, so we don't have to worry about them. So this applied force uphill has to match the 450 newtons plus the force of gravity parallel. Okay, so just as a reminder, to get that, I'd have to calculate the force of gravity down. Okay, so that would be, in this case here, yeah, it's 2,000 kilograms times 9.81. Okay, so here, let me switch this back to black. If you can just follow this here, this would be, 19,620, okay, newtons. And, oh, here, let me move that up so you can see that. And I need to find the force of gravity parallel. So with this, the angle of the incline being 6 degrees, then this little angle inside here is also going to be 6 degrees. And so I can find, I'm going to move over here. So the cosine of 6 degrees, multiply that by my hypotenuse, which is 19,620. And I get a force of gravity parallel, which would be this. I'm sorry, I use cosine. That's not right. I should use sine for that, because I need the opposite. They need the opposite value. Okay, so that should give me 2050.85. Okay, and that's getting this part here. I guess I'm highlighting that there in black. That's the force of gravity parallel. So I get that, and I already know that there's essentially friction. This question could have a little more clarification because there's probably some other friction there, but it doesn't say there is. So then the total forces downhill would be this 2050 plus the 450 newtons. Okay, so then that gives me 2.50 times 10 to the third newtons, or 2.5 kilonewtons, I guess, if you really want. Okay, so this would be the force needed uphill to So we'd have that force going uphill, and that would counter down all the forces downhill, and that would be necessary to maintain a constant speed. Okay, so a little bit of work there, but the point is that you could find what the force uphill would be, the forward force we needed to maintain the car speed. Now, this last question is actually one that deals with calculating power if you're moving at a constant speed. So now that we know the force, it says, assume that all of the power output goes into maintaining the car's forward motion. Calculate the power output of the engine. So we're just assuming that it's basically 100% efficient. And so if we're going to calculate power, if you can recognize, and there won't be too many questions, but if you get a vehicle or an object that's moving at a constant speed, that should be a little reminder in your head that you could, if you had a constant force, you just have to multiply that force in newtons by the speed in meters per second, and you will get Newton meters per second. But a Newton meter is a joule. Okay, so as soon as you're getting joules per second, you're getting power, you're getting watts. Okay, so I mean, that math here is pretty straightforward. You would go, the force is 2.5 times 10 to the third, and you'd multiply that by the 25 meters per second. And that, I think it comes out to 62,521.25 watts, which we could simplify that probably just to 62.5 kilowatts. Oops. Okay. So yeah, there would be a simple application of determining power. So I'll post the answers to these shortly. I don't even necessarily want you to do them all because I'm going to give you some more review in a bit anyway. So if you would just do questions 1, 2, 3, 4, and 5. Let's just do 1 through 5 on this page here, and I'll post these answers. Oh, yes. I skipped over that. Question 1 says, what's the power output of the crane? And then it says convert the SI unit, so the System International, or just the metric, right? Converting watts, convert it to horsepower. Well, I forgot to mention that up here. A horsepower is 746 watts. That kind of became the standard metric conversion. Okay, and we still use horsepower. We're talking about cars mostly, or small engines. You'll still see that they're measured in horsepower because that's just a conventional unit. So, but yeah, for this question here, you could once you get your answer, you could say 1 watt is, or sorry, 1 horsepower, sorry, is 746 watts. Okay, so anyway, off you go. I'll try and post these soon, and there'll be some more review questions coming. So anyway, keep up the good work, you guys.